All right, we've got a story problem here with periodic functions. I've set up some axes and we'll fill in what's missing here together as we read through this. It's talking about the moon's distance from Earth varies in a periodic way that can be modeled by a trigonometric function. When the moon is at its perigee, perigee being the closest point to Earth, it's at 363,000 kilometers away. When it's at its apogee, farthest away from Earth, so think maximum distance, it's 406,000 kilometers away. The moon's apogee, that max, occurs 27.3 days apart. So every 27.3 days, it's going to get to that max distance again. The moon reaches its apogee on January 2nd at 2016. Find the formula for the trig function that models distance between Earth and the moon t days after January 1st. Define the function using radians. All right, so you see on my axes here, I first of all broke the y-axis so that we could actually talk about such high values and still see my x-axis here close by. I am making a note down here as well. T equals 0 represents January 1st, and that would make sense to call t equals 1 day later, January 2nd, since they are talking about t days after January 1st. So our first apogee, they said, is on the 2nd. So I place this coordinate here at 1 day, 406,000 kilometers. And my next point I'm going to place is another apogee. And again, this is not to scale. Well, maybe I should move that point a little further out, just because I'm just going to give it some room here. So let's put it way down here. And that is 27.3 days later. So I can label this, it's kind of a funny point. I know the coordinate is 406,000 kilometers for the y value, but what we have to do is talk about the period. So it returns to apogee every 27.3 days. So 1 plus, if the period is 27.3 days, then this coordinate that we get up here is going to be 28.3 days. It would be my x value. Okay, so we have some exact coordinates now. The perigee, since this is cyclic, and they did say it goes with the trigonometric function pattern. The minimum between two maximums is exactly in the middle. So whatever is exactly in the middle of 1 and 28.3, that x value, or that t value, I guess in this case, we're going to have to figure out what is half of that 27.3, and we'll be able to start getting some detail here. So half 27.3 would be 13.5, so 13.65. So 14.65 comma 363,000. Okay, so half of that 27.3 was 13.65, and then I just added that to 1 to get my x value. Okie dokie. So there's some things we could do here. We could find the midline. Okay, that's the middle of the wave curve that we're looking for here. And we could do that by taking, well, first it's actually going to be easier to find the amplitude. So I'm going to go and calculate amplitude as 1/2 the total height. Okay. So the total height is just the difference in apogee and perigee. So what is the difference between 406,000 and 363,000? Okay, that is 43,000. So whatever half of 43,000 is in this case 21,500. So our amplitude, 21,500. 1,500. Okay. So we could start writing out our trig function because we know the amplitude is going to be 21,500. These are kilometers. But we were doing this to figure out midline. So remember, midline can be calculated as maximum minus amplitude. So maximum here was the 406,000, and the amplitude we just found, 21,500. And I'm going to use my off-screen calculator just to quickly get that. $384,500. So our midline, also known as our vertical shift, is 384,500. Okay, so that's this value here. And I can add that on to the end of the model that we're creating. Like I said, that's our vertical shift constant. Okay, now we need to start placing or deciding, is this a sine or a cosine? So if you're at the top of your cycle here with that first anchor point we had, it has nowhere to go but down. It'll cross the midline, it'll bottom out, it'll cross back through the midline, and it'll top out again. So as you tidy this up and kind of sketch the situation, you can see this very much looks like a cosine curve. And that's me focusing on that first high anchor point, which is typically right on the y-axis, but in this case, it's been shifted over 1 unit. We call that a phase shift. So there'll be 1 unit right, will be x, pardon me, t, keep my variables straight here, t minus 1, and as I mentioned, this is going to be a cosine. All right. Now, I left a little space up front here in case we needed a negative on our leading coefficient. Here we do not. That high point for cosine should be up at the top there, and we recognize it there. So we do not need a negative placed on the front there. The only thing left to do is find that b value to get this period correct. So remember, b is equal to 2 pi divided by 1 period. And the beautiful thing about this problem is they gave us the period. The distance between apogees is like saying the length it takes to complete one cycle, because every time it gets back to apogee, that is the amount of days it takes to cycle through all the distances. So 2 pi divided by 27.3. And you know what? I'm going to just leave it like that. I'm not going to reduce that fraction or make it a rounded off decimal. I'm going to just supply this as my b value, which is one of the nastier b values we've ever run into. So type that in carefully, but that is the model I get to fit this situation.